How on earth does Kate manage to do this? I mean, what is this? What is it for?
Do I spy some DNA?
I'm trying to make a nucleic acid, but it turns out it's much more complicated than I thought.
Does that mean you need my help?
Ugh. Yeah, okay, I need your help.
No problem. I can show you, and we can show them, how to build a nucleic acid. Join us this week on DNA Decoded. Today, we are going to build a polymeric biomolecule step by step.
9 syllables? Kate, you're over your limit.
Okay, fine. Today, I'm making a polymer, a type of long chain-like molecule in our cells. It's really just a large molecule made up of smaller units called monomers. Our cells are made up of many polymeric molecules. Proteins are one example, nucleic acids are another.
Nucleic acids actually come in 2 flavors, DNA and RNA. DNA is an acronym. We learned before that the D in DNA stands for deoxyribose, which is a fancy name for the sugar in the rails of the ladder. Now we know where the Na in DNA comes from. Na stands for nucleic acid. We'll get to the RNA later.
Both nucleic acids and proteins are manufactured in a similar process. It involves building a long chain from basic building blocks.
I see. We already know that DNA monomers differ in their 4 nucleobases, A, T, C, and G. These are the rungs of the ladder. Each rung is made up of the Watson-Crick base pair where A pairs with T and C pairs with G.
We can add a sugar and a phosphate to A, T, C, and G to create a nucleotide.
And if we start adding nucleotides together, we start to see our DNA ladder take shape. So to recap, we end up with our DNA polymer by piecing together monomers.
Yep, and here's another name for you. Each of these monomers is called a DNTP.
Kate, too much terminology here.
Okay, I'll get to that later.
You'll notice that the monomers really like to stick together. The sugar and phosphates form covalent bonds. These bonds are super strong, like crazy glue. These strong bonds occur only when there is an exchange for energy. The chemistry of this is slightly complex, but the key to this reaction lies in the 3 linked phosphates in each DNTP. If we want to link monomers together, we need energy to drive that reaction. Luckily, the phosphates are like super tight springs ready to explode and burst with energy when they're released. For the monomers to come together, 2 phosphates are released to give us the rail of our DNA ladder.
Wait, you're telling me that we have to lose 2 phosphates in order to make a super strong bond? That's counterintuitive.
Yep, that is exactly what I'm telling you. That's biochemistry for you. The 2 complementary monomers that contain our nucleobases in DNA are stuck together too. But remember that the links between them are weak, non-covalent interactions. That makes it easy for a DNA strand to be unzipped, but we'll get to that later.
Just another bit here. It may look like the strands are running in the same direction, so parallel. But actually they run in opposite directions.
So anti-parallel.
Exactly. Scientists use a distinct numbering system based on the location of specific chemical groups to indicate this phenomenon.
For example, we say that one strand runs in the 5' to 3' direction, while the other strand runs in the 3' to 5' direction.
Don't get caught up in the jargon. Just remember that the strands must run in opposite directions for the DNA double helix to come together.
So there you go, how to make a DNA polymeric biomolecule.
Too many syllables, Dr. Felicia.
Yeah, I know, but they get it now. Let's go eat.
Well, you didn't think I would let this video end without taking the opportunity to tell you more about DNTPs, did you? Of course not. I realize that in science, at times, the jargon can get overwhelming. But DNTPs are super important. So let's take a minute to talk about them in depth. DNTP stands for deoxynucleoside triphosphate. And this name will make more sense if we look at the structure. Now, we've already talked about the deoxy bit. The D in DNTP and DNA stand for deoxyribose, or D sugar. Now, what about the N, the T, and the P? Well, nucleoside sounds super fancy, but it's just another way of saying our nucleobases, A, T, C, G, are attached to the sugar. Sugar plus nucleobase equals nucleoside. That just leaves the T and P, which simply refer to the 3 phosphate groups, the triphosphates. These groups are packed with energy, which helps drive the formation of DNA strands. See, the jargon isn't so intimidating when we take it bit by bit. Caitlin out.